start with week 7 tutorial. The first question is you have to choose the correct air passage from inlet to outlet of a turbojet engine. So here this we have discussed earlier. So you know the answer is so first you have the intake, diffuser, compressor, then the combustion chamber, then turbine, and then the nozzle, right? So this is the schematic of a turbojet engine here. So the answer is this one: intake, compressor, combustion chamber, turbine, and nozzle. Okay. Then then what is transmission efficiency of a turbojet engine defined as? What is the definition of transmission efficiency? Yeah, compressor work to turbine work. So basically, yes. So basically, there is some amount of work which the turbine is producing, and ideally, we want all that work to be transmitted to run the compressor, but there will be some losses during the transmission. So that is what we define as the transmission efficiency, which is compressor work to turbine work. Okay. The next question is, for a given maximum cycle temperature, the specific thrust of the ramjet engine is. How does it vary with the Mach number? Okay, so like you know about the ramjet, right? So in ramjet, yeah, sorry. Yes. So it first increases and then it decreases. So this is the answer. And this what I've shown here is the schematic of ramjet. So we have discussed this also earlier. Initially there will be some intake, okay, and you'll have these system of shocks sitting at the intake, which will convert the supersonic flow to subsonic flow. Then in the combustion chamber, basically in this area, combustion will happen at subsonic speeds, and then we have a nozzle. Okay. So what the question is that if the maximum cycle temperature is fixed, so that is whatever maximum temperature you can achieve after the combustion, that is fixed, then how does the specific thrust change with the Mach number? So what happens is that initially, as you increase the Mach number, you'll see that the specific thrust is increasing, but after a certain Mach number of around 3, you'll see that this specific thrust starts decreasing. Okay. Similarly, we can ask what happens to the specific fuel consumption of the ramjet engine as we increase the Mach number. So what is the answer? Continuously decreases with Mach number. Yes. So why is that so? So as you increase the Mach number, basically the specific fuel consumption is decreasing. Why? I can't hear you. Your voice is breaking. Okay. Yeah, specific thrust is increasing, so the specific fuel consumption is decreasing, or you can basically say that, see, as you increase the Mach number, the strength of these oblique shocks is going to increase, okay, and as a result, the compression is going to be strong across these shocks. So the temperature which is reached even prior to the combustion chamber, that is increasing. So now you need lesser fuel to raise the temperature to the maximum engine temperature. As a result, the specific fuel consumption will decrease. Okay. Yeah, so then the next question is turbofan engines. You have to compare the propulsive efficiency and the bypass ratio of turbofan engines and turbojet engines. So which one has higher propulsive efficiency? are higher, right? Yeah. Okay. In the ramjet engine, combustion takes place at subsonic or supersonic speed. What is it? No. So see, yeah, subsonic. So subsonic combustion happens in ramjet, and in scramjet, combustion happens at supersonic speeds. Okay. Yeah. So be very careful while these questions are pretty simple. Okay. So now there is a numerical. There are some inlet conditions given, compressor pressure ratio, and all these things are given, and the efficiency of each component is given for a turbojet engine. Okay, and they have also given that this turbojet engine is operating at a Mach number of 0.7 at an altitude of 8,000 meter. Okay, so all these values are given, which are needed for calculating the turbojet engine cycle. Okay, and then we have been asked to calculate some of these quantities, such as the real total temperature at the outlet of compressor, then turbine outlet total pressure, and so on. So basically we need to solve the cycle. Okay, so how do we start? We'll start by noting down some important parameters. Okay, so first we are given compressor pressure ratio, right? So that is P naught 3 by P naught 2 is given as 8. Okay, then we are given combustion efficiency, compressor efficiency. So I'll denote compressor efficiency as eta C. So here is isentropic efficiency of the compressor. This is of turbine. Then for the intake, which is nothing but the diffuser, so I'll call this as eta T. Okay, and for the nozzle we have eta N. Mechanical transmission efficiency is also given, so eta T. Combustion efficiency is I'll call this eta Cc. Okay, and then the combustion pressure loss. Okay, so in the combustion chamber we usually assume that the pressure remains constant, but now they have given that there is some combustion pressure loss also. So there will be basically, if you start at P naught 3, ideally you would assume that P naught 3 is equal to P naught 4, right? But now there is a loss. So what is that loss? It is P naught 4 will be 0.96 times of P naught 3. Is this okay? Is this clear? Yeah, okay. Okay, so yeah, all these values are given. So let us just start calculating the across the compressor. So the first thing we have to calculate is T naught. So T naught is so wait, let me just draw the cycle first. So yeah, so just help me draw the cycle first. So how is the TS diagram going to be? So let us say the state 1 is and I'll start with not 1 state, that is the stagnation state, which is just before the compressor. From there, across the compressor there will be an increase in temperature and increase in pressure. So let us say this is the pressure line, isobaric line. Okay, and then in the combustion chamber the pressure is supposed to remain same, but it will reduce slightly. So this will reduce slightly to 0.3, and then this is for the turbine. Okay. Okay, so now I'll just rename these pressure values also accordingly. So the pressure ratio RP is P02 by P01 over here, and that is 8. And in this ideal situation, you will have P03 is equal to P02, but because we are given a combustion pressure loss of 4%, there will be P03 is basically 0.96 times P02. Okay. So now tell me what is the equation for T01, because remember we are given the inlet conditions that at 8000 meter altitude the temperature is given to be 236.2 Kelvin, speed of sound is given 308 meter per second, and also the pressure is given at this altitude. So we can calculate T01 as T1 plus, what is the formula? Yeah, but see that, okay, what you're saying is T1 I have to take common, that is 1 plus, yeah, can you repeat that? T1 plus C square by 2CP, right? Yeah, so now we know the speed of sound C, and we know T1, and CP is also given. So if you just plug in these values from here, CP, which CP will you use? So for the compressor, only air is going through the compressor. Okay. Yeah, so we will be using this value 1.005. Okay, so if you just plug in these values, what is the value of T0 that you get? Please calculate and tell me. So this is 236.2 Kelvin plus C square is given to you as 308 meter per second by 2 into Cp, which is 1.005 in kilojoules, so you'll have to multiply 10 by 3. Okay, 1 second. So this C is given, I made a mistake here. A is given to you as 308 meter per second. So what is C? What is the speed of sound? Speed of the inlet flow. It's going to be the Mach number. Yeah, Mach number times the speed of sound, and then the square of that. And what is the Mach number given to you? 0.7. Okay. Yeah. So now what is T01? Answer? Yes, 259.34 Kelvin. Okay. Now also we know what is the pressure at the inlet. So P ambient is given to us, right? So what is P ambient? It is given to be 0.3565 bar. So I'll just write that here. So we can calculate P01, right? So what is P01 going to be? PA multiplied to 1 plus eta intake, that is eta diffuser, into C square divided by 2 Cp T ambient, the whole raised to the power of gamma by gamma minus 1. Is this formula clear? Yeah, so you must have seen the derivation of this formula in the lectures also. So now you have the value of Pa over here. Diffuser efficiency is given, and again C is equal to Mach number into the speed of sound. Cp you will use for air, and T ambient is also given to you. So if you plug in all these values, P01 turns out to be, so I'll just give you the answer over here. It is 0.4837 bar. Okay. Now at the outlet of the compressor, we can simply calculate P02, because P02 is going to be the pressure ratio Rp multiplied to P01, right, and that was given to be 8. So P02 is 3.8698 bar. Okay, so now comes an important thing. If I have to calculate the temperature at the outlet of the compressor, so what is the next step? I need T02 at the outlet of the compressor. So how do I calculate that? Right, so first you will use the isentropic relation. So first let us calculate T02s. Okay, so T02s by T01, you can calculate that because you know the ratio P02 by P01, and that to the power of gamma minus 1 by gamma. Okay, if you do this, you will get T02s, and then we have the efficiency of the compressor, which is what? What is the definition of compressor efficiency? It is the ideal situation by the real situation, right? So it should be T02s minus T01 divided by T02 minus T01. So you know T02s from this isentropic relation. T01 we found above, and the compressor efficiency is given. Okay, so what is the compressor efficiency given to be? 0.9. So if you just plug in all these values, you can obtain T02. So what is the answer? What is the answer for T02? You can basically combine these two formulae and write a single formula if you can remember. Yeah, tell me the answer. T02 is? No, that's not the answer I have. No, please try it again. Yeah, so I was saying that you can combine these two formulae and basically rewrite for T02 as T01 plus T01 divided by eta C into the pressure ratio Rp to the power of gamma minus 1 by gamma minus 1. Okay, so basically you put this T02s in terms of the pressure ratio in the definition of eta C, and then you rearrange to find T02, so you will get this formula. Okay, so the answer I have over here for T02 is what I got is 493.16 Kelvin. Okay, yeah, so I wanted the value of T02. Okay, so what T02s you were getting as 470 approximately. Okay, fine. Okay, then the next thing we can do is we can calculate for the turbine. Okay, now understand what we are given already is that the maximum temperature, that is the turbine inlet temperature, is given. So this is nothing but my T03 real. Okay, and also I was given the pressure ratio, so I can find P03, and you have P02 over here. So what is P03? Sorry. So you have P03 is 0.96 times of P02, and we found P02 already above, right? So what is P03? Can you just quickly calculate and tell me the value of P03? Am I audible still? Yeah, okay. 3.7148 bar. Alright. Then the next thing is T03 is given to me as 1180 Kelvin. So we can now find what is the value of T04. Okay, so for that, again I'm given the turbine efficiency. So using the turbine efficiency and using isentropic relation, so first we can have T04S by T04 is equal to P04 by P03, and this to the power of gamma minus 1 by gamma. So you can find T04S, then plug it into the definition of eta T, and then find T04. Okay, so T04 turns out to be 962.16 Kelvin. So what I'll do is I'll just give you also the formula that you get if you plug in this value into the eta T. So what you have to do is you write eta T as T03. So what will be the definition of eta T? It will be T03 minus T04 divided by T03 minus T04S. Am I right? Yeah. So now if you just plug in this value of T04S in terms of the pressure ratio of P04 by P03, so you can rearrange and get that T04 is actually equal to T03 minus 1 by eta T into T0. Okay, I think you'll have to take T03 common, and then so you'll have 1 minus T04S by T03, but that is nothing but, okay, this is 3, this is nothing but P04 by P03 to the power of gamma minus 1 by gamma. Okay, and then basically you put all the values and get the value of T04. So is this part clear? Okay. Okay, so in this question, what are we already given? What is given to us? P03 is given, T03 is given, but we do not have the value of P04. So how will you find the value of T04? I shouldn't have given this value here to you. So you have T03, you have P03. How will you find T04? Any idea? Hello? Hello? Yeah, I can't hear you clearly. Maybe speak a little more loudly. Okay. Sorry, T naught, not T naught 1, we need T naught 3, T naught 4. Okay, maybe I'll just tell how to do it. So you can rewrite this, you can rewrite it as T naught 4 is equal to T naught 3 minus 1 by eta t into T naught 3 minus T naught 4 s. Okay, and T naught 4 s is nothing but T naught 3 minus Cp air by Cp gas into T naught 2 minus T naught 1 divided by the eta transmission. Okay, so how did we get this formula? This is by saying that the work of the turbine is equal to eta transmission into work of the compressor. Okay, so if you use this, you can see we already know T naught 2 and T naught 1, and why are we getting this Cp A by Cp gas? Because the fluid which is going into the compressor is simply air, right? So what is work of the compressor? It is just going to be Cp air into the temperature difference, right? T naught 2 minus T naught 1. And what is work of turbine? It is Cp of the gas, because now the gas is after the combustion has happened, right? So you will not use Cp air, you will use Cp gas over here, and this will be T naught 4 minus T naught 3, right? Is this clear? Hello? Okay, okay, and what did you get for T naught 4 then? So your answer is right for T naught 4s, which was some 973. Yeah, so T naught 4 is 962.16 Kelvin. Okay, so now we can, because we know T naught 4s, we can go back to this isentropic relation and we can get the value of P naught 4. Okay, so P naught 4 turns out to be, and again remember which gamma will you use in this particular relation. Here gamma you will use for the gas, not for the air. Okay, okay, so P naught 4 value is 1.6412 bar. Okay, then I think we have done most of the things they have asked. They asked us to calculate the total temperature at the outlet of the compressor, which is what? T naught 2. Then the turbine outlet total pressure, which was P naught 4. That's done. Okay, then we have to calculate the critical nozzle pressure ratio. So what is critical nozzle pressure ratio defined as? Do you know the definition? No? Okay, so nozzle pressure ratio is defined as P naught 4 by PA. So this is nothing but the stagnation pressure. So remember that in a nozzle, there is no moving part, right? So whatever is the inlet stagnation pressure is going to be the outlet stagnation pressure, right? So P naught 4 is basically equal to P naught 5. Okay, and ambient pressure is the actual pressure in the atmosphere, and ideally we expect that your turbojet engine should expand the air into the atmosphere, so the stagnation pressure should ideally be equal to the ambient pressure, right? So we expect this to be 1, expected 1, but it may turn out to be more than or less than 1. Did you understand that? Yeah, so if you basically put the value of P naught 4 and the ambient pressure which is given, what is P naught 4 over here? We found 1.6412, and what was given for the ambient pressure, it was given as 0.3565, right? So the ratio turns out to be equal to 4.6. So the total pressure at the end of the nozzle is much more than the ambient pressure, at least 4.6 times more than the ambient pressure. Okay, so now what we need to calculate is the critical pressure ratio. So the critical pressure ratio, this definition you would have seen, is P naught 4 by PC, which is nothing but 1 divided by, it's a huge formula, 1 minus 1 by eta nozzle. So nozzle efficiency is also given to us, and gamma of the gas minus 1 by gamma of the gas plus 1, and this entire quantity raised to the power of gamma by gamma minus 1. So do you know this formula? Yeah, so this is derived in the lectures, I guess. Okay, so yeah, so this turns out to be, if you just put the definition, the values, because you know the nozzle efficiency, and you also know these values of the gamma. Here also you will use gamma gas. Okay, so you know all these values. Critical pressure ratio is basically 1.92. Okay, and what we found is that the actual nozzle pressure ratio is 4.6, which is more than the critical pressure ratio. So now what will happen? Yeah, what will happen if the actual pressure ratio is more than the critical pressure ratio? Under expanded condition, no, first thing is that the nozzle will be choked, right? So the nozzle is going to be choked. Yeah. Okay, so then the next thing we need to calculate is the nozzle outlet static temperature. So what will be the formula we use for this? So remember that the nozzle is choked. So under choked condition, how can we find the static pressure? So we know the stagnation pressure is T naught 4. We will use T naught 4S, right? And we know this, and we also know that the definition of these temperatures is what? T into 1 plus gamma minus 1 by 2 m square. So what will we use over here? What is choked condition? Yeah, what will be the Mach number? Come on, this is simple. Am I still audible? Yeah. Okay, please answer quickly. Okay, so the Mach number is going to be 1. So if we put this over here, we get, this is T into gamma plus 1 by 2, right? And gamma again you will use gamma gas. So from here you can get the static temperature T5, and the value will be 834.16 Kelvin. Okay, is this part clear? Yeah, and then we also had to find, so going back up, sorry, we also had to find, so this is the static temperature at the exit of nozzle that we have found, and then we need the specific thrust produced by the nozzle and the specific fuel consumption. Now to find the specific thrust, remember, for produced by the nozzle, what is the thrust produced by the nozzle over here? When you have a turbojet engine, we said there is some pressure applied in this direction, say PA, and there is some pressure applied in this direction, say PE. Usually we assume that PA is approximately equal to PE, but in this condition, because we have a choked nozzle, this is not going to hold true, right? Instead, the exit pressure is much higher, so there is going to be a thrust produced due to the choked nozzle, right? So thrust is what was the definition? M dot into UE minus UA plus exit area multiplied to PA minus PE. Oh sorry, PE minus PA. Yeah. So now what are we asked to do? We are asked to calculate this part, this PE minus PA. This is what we are asked, right? Yeah, so for this, what do we need? First of all, we need the exit pressure P or P5. So here you can calculate P5, which is equal to PC, which is equal to, so we found the critical pressure ratio, right? So critical pressure ratio was P04 by PC, which is 1.92, and then you know P04 from your earlier calculations over here, 1.64 bar. So if you just use that value, use that formula, you will get PC as 0.85, 8553 bar. Okay, so now we can calculate the specific thrust. So let's see. Okay, so the specific thrust force, I'll write it as Fs, is nothing but the area, the exit area, and because it is specific, so we are going to divide it by m dot, that into PC, because that is the exit pressure PC, minus the ambient pressure PA, plus what is the other term? The other term was the velocity term, right? So that is U exit. So U exit, again it is at the critical condition, so I'll write this as UC minus UA. Okay, so now we need to find these values. So we have PC and PA, we need to find UC and UA. So how can you find it? Any idea? So what is UA? We know the inlet Mach number, right? And we have also the speed of sound, so m into a. So similarly, how do we find UC? We can use this formula, right? So we know the Mach number is going to be equal to 1 under the choked condition. So Mach number is 1, that means UC is equal to under root gamma R PC, which is nothing but the speed of sound. Are you there with me? Yeah, okay. So now you can find UC, because we know this TC value. We found this TC value as 834.16 Kelvin, right? The static temperature at the exit. So, and gamma will be gamma gas, and R will also be given to you. So if you go back to the question, yeah, specific heat at constant pressure, this is given Cp, specific heat ratio, is given, and R is also given. Yeah, 287 joule per kg Kelvin. Okay. So if you just put all these values in, what do you get as UC? Just calculate and tell me. What is the value of UC? Yeah, so it is 564.9 is what I have, meter per second. Okay. Now the next thing I need to find is, okay, so UC is known, PCPA is known. I need to find this quantity AE by m dot, right? So how do we find that? So we know the formula for m dot is nothing but density into area into the speed. This is clear, right? Rho AV is m dot. So yeah, so at the choked condition, I know that m dot at the choked condition is rho C, A exit, and UC. So we know UC, and we basically need to find AE by m dot, which is nothing but 1 by rho C UC. So the only thing I don't know here is this quantity rho C, but I can find that as PC by R TC, and we know PC, we also know TC. So rho C will be what? So you know the value of PC here, it's 0.8553 bar. Put it in SI units, you know TC. So putting in the values, you find rho C is equal to approximately 0.3572 kg per meter cube. Okay, so if you just plug in all these values back into your force equation, okay, sorry, first the value of AE by m dot, so I'll give that. So you can just plug in the values and see if you are getting the same thing. So AE by m dot turns out to be 0.00495 meter square second by kg. Yeah, sorry, are you getting the same? Yeah, I couldn't hear. Can you repeat? Okay, I'll assume that you got the same. If there's any doubt, please stop me. Okay, so now you can just plug in all the values, and the specific thrust turns out to be 596.149 Newton per kg. Okay. Okay. Then the next thing we had to find was the specific fuel consumption. So specific fuel consumption is defined as what is specific fuel consumption defined as? Hello. Okay. Okay, fuel air ratio divided by the specific thrust, right? So that is fuel air ratio divided by this Fs. So this how will you find the fuel air ratio? We have already found this earlier, no? How will you find the fuel air ratio? Is it given in the question? Okay, let's see. Yeah, so they have given you a theoretical fuel air ratio. Okay, what if you're not given the fuel air ratio? How will you do it? Ideally, what you would do in that case is you will balance the work by the compressor and work by the turbine. Okay, given the transmission efficiency, accounting for all that, you'll basically do balance of work. And while writing the this work equation over here, you will write m dot. So there will be, over here there should be an m dot air term, and here there should be m dot air plus m dot fuel term, right? Now because you were just taking a ratio, and m dot f was very very small, so you neglected it over here, but ideally you should account for that in the calculation. Okay, and then by doing that work balance also you can get the fuel air ratio. So right now, since the value is given and you have already found the specific thrust value, so yeah, you can just get the answer of specific fuel consumption is 0.1171.